Hello everybody, welcome to the 6.1 through 6.2 notes. These are part 1 of the notes and then you'll get part 2 later. So this whole unit is going to be about integrals, definite integrals, indefinite integrals, and another word for them is the antiderivative, and that's what we'll figure out later. The opposite of the integral is the derivative. The opposite of the derivative is the integral. So just to start with, I'm going to draw a little sketch of a function right here. Just a curve. So I'm going to call this f of x, and then I'm going to be concerned about the function from, let's say, a to b, and say I want to find the area under this curve. So the way that we are going to talk about the area under the curve, we could say, oh, find the area under the curve of f of x from a to b, right? We could say that every single time, but that's a little bit long, and so mathematicians came up with this notation called the integral that will help us say the notation under the curve a little quicker, and that's called the integral. So the integral looks like a long S like this, and what you're going to start off with is you're going to write your function here, so f of x, and then you're going to write dx, which is, we'll kind of understand and break that down later, what the dx part means later. But then you're going to put your lower bound on the bottom and your upper bound on the top. So what I mean by that is the number that is comes first in number wise, right? The smaller number you're going to put down here. So a, and then you're going to put b up here. So these are the bounds, right? So you want to find the area under the curve of this, right? You want to find the area under the curve. So that's what you're putting, whatever the curve's function is, you're putting that here. And then you're putting from A to B here. And essentially what this means, and I'm just going to write it out. I mean, I've said it a couple times, is this notation means area under curve f of x from A to B. And so what we're going to be doing eventually is we're going to be able to figure out exactly what the area under the curve from A to B is, depending on the information we're given. But today we're just going to start with approximating it so we can kind of understand and start developing the idea of an integral. And so the 6.1 part 1 notes are going to cover right Riemann sum and left Riemann sum. So that's what we're going to do today in these notes. But tomorrow, or the next notes, we're going to do the midpoint Riemann sum and the trapezoidal Riemann sum. So basically what we're going to do, this function right here, it's not going to be cut off for you, but it got cut off for me. This function right here that I have is x squared plus 1. And it says approximate the area under the curve, so under x squared plus 1 on the interval 1, 3. So again, we're approximating 1, 3 using right endpoints, or right endpoints of 4 subinterval of equal length. So what that means, if you see the word right endpoints, that should be pointing you to the right Riemann sum. That's the fancy word for that. And so things that I'm learning about this is that we want to figure out the area from 1 to 3. So if I go over here to this graph, I'm concerned about the area from here to here, basically. And I might erase that later. So if you just drew that, maybe just do like a dotted line for right now. Okay, so I want to find the area from 1 to 3, and it says it wants me to use 4 subintervals of equal length. So that means it wants me to use 4 rectangles, and that they're all going to be equal length, okay? So if they're going to be equal length, we have from 1 to 3 to make these rectangles, and we need 4 of them, okay? So I'm going to figure out what should the width of each rectangle be. And so the notation I use is the change is delta x to use this. And so I'm going 3 to 1, and then I want 4 rectangles. And so 2 over 4 equals 1/2. So the width of each rectangle is going to be 1/2. So that's just like us setting up our work. And then it says that it wants this to be a right, so this is where the right Riemann part comes in. It says using right endpoints. So what that part means is I'm going to draw a picture here in a second, but we're going to start at 3 because of the 2 endpoints, 1 and 3, 3 is the right endpoint. So we're going to start there. And so I'm going to go ahead and draw my picture. I'm going to draw 4 rectangles starting at 3, and each rectangle is going to have a length of 1/2. So I'm going to start down here and I'm going to break these up. So if I have 4 rectangles, each with 1/2, I'm going to make this a little smaller, but this is 1/2, right? So this is going to be 1 rectangle right here. Another rectangle is going to go from here, and then this is 2.5. And sorry, this should say 1.5. So I have 1 rectangle, 2 rectangle, 3 rectangle, 4 rectangle, okay? So those are my 4 rectangles. Now I'm going to draw them. So if I'm drawing a right rectangle, what I'm going to do is I'm going to start at my endpoint 3, and I'm going to go all the way up till I hit the curve, and then I'm going to go over a 1/2 unit, okay? And I'm going to go ahead and darken my marker again. So I'm going all the way up till I hit the curve, and then since the rectangle is supposed to be 1/2, I'm going to go halfway, and I'm going to drop down till I hit 2.5. So that's my rectangle, okay? And then I'm going to do this process again. So I'm going to go up from 2.5. That's going to hit right here, basically, and I'm going to go over a 1/2, and then I'm going to go down. And I'm basically going up from 2, which goes to right there, and then I'm going over a 1/2, down, and then one more time, up. That's how my rectangle is going to look, like that. So up like this. And so I've created 4 rectangles. Okay, and so I'm going to use those 4 rectangles to approximate what the area under the curve is, because I don't really know an area formula for like this weird curve situation, but I do know what the area formula of rectangles are. Now this is approximation because if you notice, there's like spaces that are missing out or that are going over, right? Like these 4 spaces are over the curve. So obviously my approximation is going to be an overestimate. I can go ahead and write that down right here, but we're just approximating for right now, and we're going to figure out as we go on how to make these approximations more accurate. So to set this up, to actually figure this out, I'm trying to find the area under the curve from 1 to 3, okay, of f of x dx. And that is going to be approximately, so basically what I'm doing is I'm just finding the area of everything. So the area formula is length times width, so I'm going to do 1/2 because that's what the widths are. And then I need to figure out what the height of this rectangle is. And the height of this rectangle is basically whatever f of 1.5 is, because that's what this point here is. It's just whatever the y value is at 1.5 if I were to plug it into this equation back up here. And so for right now, I'm just going to write f of 1.5. And the next rectangle, the width is also a 1/2, but then this rectangle's height is defined by 2. So whatever f of 2 is, that's going to be the height of this rectangle. So that's going to say f of 2. And then same kind of idea, the next rectangle's height is 2.5. And then the last rectangle's height is 3. So I should have basically 3 like area formulas when I am done having them written out. The 1/2 is the width again. The f of 1 point, whatever it is, 1.5 in this case, is the length. And because it's a right Riemann sum, when I'm done, I should see the last endpoint, the second endpoint listed. So I see 3 listed, and notice I don't see 1 listed, and that's because I used a right Riemann sum. But if I use the left Riemann sum, which is what we're going to do in a second, and we're going to do the exact same problem, I would use the left endpoint. So now I'm going to figure this out, and now from here it's just like kind of algebraic, but one thing I can do, because these all have the same width, just to make it easier and so I don't have to multiply 1/2 every single time, I'm just going to factor it out, and then I'm going to find all of these values. That'll just make it so I don't have to multiply 1/2 like 4 times. And when I go to find these values, I have the equation of the curve, and so I'm going to be plugging these into the equation of the curve. So I'm going to have 1/2, and then f of 1.5, I'm evaluating using the equation, which is x squared plus 1. So I'm going to write 1.5 squared plus 1, and then, plus 2 squared plus 1, plus 2.5 squared plus 1, plus 3 squared plus 1. And so I will add all that up, and for the sake of time, I'm just going to tell you what the answer is. The answer to that, if I did all of this math right here, is going to be 25.5. And I'm going to take a second real quick and just check that that's actually correct. And feel free, as I pause and do this, feel free to do the same. Make sure that our work that we're doing is correct. I'm just typing it into Desmos real quick. That should be correct. And so our approximation for the area under the curve from 1 to 3, so we're basically approximating this space here from 1 to 3, it's going to be 12.75 units squared. But again, like we said, that's an over approximation. So the next one we're going to do, so feel free to pause if you need any more time writing that down, or write down some questions if you need them. But the next problem is the exact same function, but this time we are doing the left approximation. So same idea as like before, we're approximating from 1 to 3. And our width, just because we used this from the last problem, like it's still 4 subintervals of equal length from 1 to 3. So the width is still going to be 1/2. So I'm just going to, I don't have to like write as much out as last time since it's a really similar problem. And so now I'm going to draw my picture, and I'm just reminding you guys one more time, I'm finding the area from 1 to 3. And the reason I know that is because it says from 1 to 3. But this time I'm starting with the left interval. So before I go, I'm going to go ahead and mark like where my different rectangles will be, because they're each 1/2. So I'll have 1, 2, 3, 4 rectangles, but I'm starting from the left endpoint this time. So I'm going to the left, and then I'm going to draw my line until I hit my curve. And once I hit my curve, I'm going to make a like 90-degree angle, and I'm going to draw my rectangle like this. And then I'm going to keep this process going until I have 4 rectangles and I hit 3. Now this time, the last rectangle was a little ugly, but it'll be okay. So this time, notice it's an under approximation. All of this, when I go to, I'm basically finding the area of these 4 rectangles, but these 3 spaces that I just drew right there, those aren't going to count. And so this one's going to be an underestimate. This one's going to be an underestimate. And so I'm going to go ahead and write my integral out. I'm approximating the area under the curve from 1 to 3. And all of their widths are 1/2, but this time, since I'm starting from the left, the number, like the length of this rectangle is now, instead of f of 1.5, it was actually f of 1, because that's what this value is right here. So this is f of 1, and then it's f of 1.5, and then it's f of 2, and then finally it's f of 2.5. So notice this time the right endpoint gets left out. And so you'll eventually kind of get the hang of this and like kind of memorize the idea here. But same idea as last time. I'm just going to factor out the 1/2. You cannot factor out the 1/2 if it said something like unequal intervals. And normally you'll have a table when you're asked to do that. So don't like overthink that too much. But then again, I will plug all of these into this equation. So it'll be 1 squared plus 1, 1.5 squared plus 1, 2 squared plus 1, and then 2.5 squared plus 1. And this one, I guess I'll just work it out so we can check. So 1 squared plus 1 is 2. 1.5 squared is like not that hard, but I just can't do it right now. 1.5 squared is 2.25, so this will turn into 3.25. This will turn into 5, and then 2.5 squared should be 6.25, so this is 7.25. And so then I add all of those up. 2 plus 3.25 plus 5 plus 7.25, and I get 17.5. And then if I split that into 2, I get that this approximation is 8.75 units squared, which is pretty different from the overestimate. Like those are 4 places away. And so later, like I said, we're going to learn that basically the more rectangles you have, the more accurate it's going to be. So since we only have 4, that's why the left and the right are so far apart. But maybe if we had like 8 or 12, they'd be a lot closer to each other. And so that's the left Riemann sum. And that one was an underestimate. And so this is where we're stopping today. So hopefully these notes aren't too long, but here's just like a checkpoint of the difference between using, I'm going to go through this quick because prayer is about to start. Using this is a right Riemann sum. You use, I was so close. Okay, I'll be back. Okay, I'm back. So you, if you have a right endpoint, you use slash, you start with the right endpoint. And then you don't use the left. Don't use left. And then the left Riemann sum is like the exact same but opposite. So use slash start with the left one, left endpoint, and don't use the right one. And that is all. So hope you had fun taking these notes. Have a good day.